Hello, I'm Mark Nadal, and my goal is to learn WebGL. So, what better thing to do than to try and take Unreal's Nanite concept and rebuild it from scratch? This is coming from a person who knows nothing about graphics programming. So, this is part one of my fumbling into WebGL. This is what we're going to build by the end of the tutorial. It is a green box that is splattering with some dots, and that is because there is a triangle, not quite per pixel, but random triangles that are filling in the entire screen space at very quick rates. But that's not where we're going to start. We're going to build up to it line by line, starting with the doc type of HTML, because this should all run out of the browser. We're then going to add our metacare set to make sure we're using UTF-8, just to make sure that letters are set right. It's just an HTML thing. You don't need to worry about it. Next up, we need the canvas, and we're going to set it to 500 width and height. Canvas is pretty much a programmatic image that we can use JavaScript to draw pixels on. And it works for WebGL as well as other JavaScript APIs. First, we're going to write a Vertex shader. And this will be very different for anybody who's coming from JavaScript land. A Vertex shader is run for every single point in a triangle, for every single polygon, every single vertex on that polygon, for every single polygon in the entire 3D world. And it is really the core of why you're doing graphics programming, because this code is run on the GPU itself. So this line, attribute vec2 pos for position, is going to be an x and y coordinate that lets us have this main function. GL position is a global inside of the GPU that we're going to say we want the triangle's vertex to be in this position, and vec4 is saying a vector of 4, so 1 dimension, 2 dimension, 3 dimension, 4 dimension. We're not actually using 4 dimensions in this case. So the neat thing about the GPU and graphics stuff is that it will automatically take arrays and convert them, whether you use .x, .y, .z notation, whether you use array notation of 0, 1, 2, 3, even if you do something like array times array or array plus array, I should technically say vectors, it will automatically loop through the items and add them and multiply them. Same thing whenever you just state, here's the position. If it happens to be two, x and y coordinate, it will, in JavaScript, what's called splat that out. So it makes it so much easier to do x, y, z logic, and it's all on the GPU, which is awesome. Okay. So going on, we now need to start the fragment shader. And this, I think, will make a little bit more sense. The fragment shader, terrible, terrible, terrible name, is run per pixel inside of the triangle. That's technically not correct because various hardware will do various sorts of optimizations, so that's why it's called a fragment. But you can think of it as per dot inside of the triangle. And what we're going to be doing for each pixel, that's just an easier way to think about it, is setting its color. And in this case, color is defined with 4 coordinates: red, green, blue, and then transparency. So in this case, we're just going to set everything to green, which you see on the screen is already the case. GL frag color is a global. And then precision medium P float. Just different hardware has different, I guess, accuracy levels, and you have to specify that up front. again, I'm kind of new to all this as well. All right, finally into writing some JavaScript. Well, the first thing was we have to get the canvas for us to paint things to. Then we need to get the WebGL context for the canvas, because there's other things you can do with canvas. So we have to tell it we want to use WebGL. Next up, we need to actually take the Vertex shader that we wrote earlier and pass it into WebGL. And this is just the way we declare that we're going to create these Vertex systems, and WebGL is very, very verbose. This next piece is saying, okay, what is the source code for this Vertex shader that you want to create? Well, in this situation, we want to pass the Vertex kind of instance context type, because WebGL is super verbose. And then we're going to do a document query selector against the Vertex from up here and grab the text content and inline it into the shader source. And that will then run it once we do the compile operation. Next up is this, well, we're going to check for errors, because that's just useful. Next up, we're going to do the same thing, but for the Fragment shader. Again, the Fragment shader is, think of it as being per pixel. So exact same thing as what we were doing before with the Vertex, but we're going to do it with now per pixel. We have to tell WebGL, here is the code that we want to run per pixel. Again, get the error if an error happens. Now, there's this very strange thing I still don't quite understand, is we have to like combine these things together. And I think it makes sense because in Blender and Unreal and Unity and stuff like that, you can have different materials. So I'm pretty sure this is how you'd implement like a material system where you have different Vertex shaders and different pixel shaders that get combined in different types of programs that get linked together. So we're going to attach the shader to it. We're going to attach the pixel shader to it. Then we're going to link the program to WebGL itself. If there's an error, complain, and then finally use the program. Again, I'm not quite sure why. Most of this code is pulled from another tutorial that I've copied and pasted here that I'm trying to explain. So this is slightly modified by me, but is not by me originally. Again, we just got to set all these things up. Somebody smarter than me can explain why. But if we want to get even a single triangle displayed, we got to get through this. Okay. Finally, we're going to create this buffer thing, which I don't actually wind up using in this case. But we do wind up using these triangles. The triangles need to be specified in some low-level array format that can be transferred from JavaScript land into GPU land very quickly, and that's why we're using a float32 array. Things don't seem to work unless you use this sort of stuff. And what's happening here is we're specifying the coordinates for each vertex of the triangle. So the WebGL space has 0, 0 in the middle, and then 1 going up and 1 going right. Well, sorry, X usually goes first, and then 1 going up. That's completely opposite of HTML, which is 0, 0 up here, and then 1 going down and 1 going right. So WebGL's coordinate space to me actually makes more sense. So when we say -1, we go -1 this way, and then we go 1 up here. Then this next one, okay, so this would be the first vertex. Then we don't move from here like an SVG and Canvas APIs. We're basically back at 0, and it's going to say go 1 to the right and then go -1 down. So that's the second vertex of the triangle. And then finally this last one, -1, -1, right? So if we're back at the center, -1, -1 is there. And that will be the third vertex of the triangle. Okay. We now have to do this stuff, which is saying, okay, what what is this triangle data here? What does it correspond to up here in the vertex shader? And my bad, I might have called the vertex shader a fragment. I forget. And if I did, that was wrong, because the fragment was this stuff. I might have accidentally called the vertex a fragment, but I'm not quite, hopefully not. So we have to tell WebGL that this attribute right here, the very first line that we started with, is connected with these data points here. And more WebGL verbose magic. I ask somebody else about this line here. I think it tells it how many items to skip if you have extra data, and weird stuff like that. Okay, now finally we're going to get to request animation frame. We're going to create our frame that loop where we then call the next frame before we do anything else to keep as fast as possible. And we're going to do this crazy thing, gl.bufferdata array buffer, which was this thing from before, so maybe that is why we had to do it. And then tries the triangle here, and we're going to call this thing called static draw, which just gives it information how we want it to be drawn. And this is the most important piece right here. gl.draw arrays as triangles. I don't quite know what that is. And then try.length divided by 2, saying that we're only working with 2-dimensional data. Because if it was 3-dimensional data, we need 3 coordinates, x, y, and z, for each vertex. And so we have to tell it the length of the triangle divided by 2, and that will basically divide it where we have these spaces here. Okay, let's run. And this is going to be the hello world triangle, not this stuff. Boom, there you go. That's pretty cool, right? We have, in 61 lines of code, your first hello world GL triangle, where it starts at -1, 1, goes to 1, -1, and then goes to -1, -1, and it sorry, again, that's what this fragment shader is, sorry, the vertex shader is doing. We passed it the position, and then just filled out nothingness in this other data. You'd use that for 3D data later. And then we told it to color it 0 red, 1 green, 0 red, solid alpha, solid transparency. So it's not transparent. Solid opacity, yeah. So that hopefully is a good introduction, but now we want to do towards Nanite-like stuff. I spent several months trying to play around with perfecting how to place a triangle on screen after this initial demo here. And I realized, as of 2 days ago, I kind of wasted a bunch of time because I should have just gone crazy. And that's what we're going to do now with this Nanite idea. We're going to instead create a triangle we're going to create 100 triangles. So 2 times 3 is saying that there's 2 coordinates per vertex, per corner on the triangle, and there's 3 corners on a triangle. So then we want to have 100 of those. Okay. Then math.mix is this little function that I find as being useful, and ultimately WebGL provides this inside of the shader, but you'll get to that later. So I just polyfill it into JavaScript really quickly, and it basically says if we want to get some sort of number between 0 and 1, imagine we have a number between 0 and 100, and we say 50. Because all of WebGL coordinates are in decimals, we want to convert 50, which is between 0 and 100, into a decimal number, and that would be 0.5, right? Now, you might have weird offsets, like what is the number between 7 and 32 if the number is like 10? Well, we know that 10 is close to 7, so I'm guessing that's like, around 0.2, 0.1, something like that. And math.mix just lets us do that. We tell the A starting range, the B ending range, and then the M middle number in between. Then we're going to create this randomize function. Oops, I actually don't need any parameters there. And we're going to say start at -1, get the length of the triangles, and we're going to have a step size of 0.1, which is just going to define the size of our triangle. Then we're going to create a while loop, and we're going to while loop over 100 triangles. And we're going to select a random x-coordinate, and because that x-coordinate is between 0 and 1, and WebGL is actually between, -1 and 1, we want to make sure that the randomness also goes to the left side of the screen, not just the right side of the screen. So we'd basically take a random number between 0 and 1, and then we mix it such that it's actually between -1 and 1. Hope that made sense. Do the same thing with the y-coordinate. Then we're going to say for the 0, so n is -1, plus n is 0, so the 0th triangle, make it equal to x, and then make the next item in the triangle be equal to y, which is the same thing that we're doing right here, right? So x-coordinate, y-coordinate. But now we need to do this for all 3 corners. So plus n again, x plus s, and that's because the second corner we want to draw, we want it to be not at the same place. So we're basically saying move to the right a little bit, and then same thing with the y, move up a little bit, and then we're going to do the last thing where we then move to the right twice the amount as the first number, and then keep y at the same level as the first number. Now all we have to do is type in randomize here, and we'll get the thing that we ended with. We're basically, every single frame, we're filling in this triangle, this 100 triangle arrays with random coordinates. And this one, I'm starting with a larger size, so it's going to look different than the first time. So now it's a little bit more obvious what's going on. We have 100 triangles just randomly blipping around. And now finally, we're going to add more triangles. We're going to set the size of these triangles to be a lot smaller. You'd want to set them to be per pixel. And now you probably can't even see them. It's probably not even getting encoded. They're so tiny. So we're just going to say we want more than 100. We're going to do 100,000 every single frame. And Firefox actually does that really, really, really fast. I can even go up to 1 million, I think, pretty easily in Firefox. So 1 million, yeah. Let's hit that. And it's going to look solid. Isn't that crazy? It's looking solid because we're rendering almost a triangle per pixel, and you can't see it stuff. So I'm going to step back down to this other one, and that makes it a little bit more obvious because you see some noise going on. Well, there you go. This is part 1 of me trying to move towards like a nanite-like concept, but needing to, from the very start, explain to myself and to you how to even get started with WebGL. So I hope this was fun and useful.